Okay, welcome to lecture 36. So today we're going to look at an application of plane autonomous systems. And so this is a really common application that if you study third year mathematics 16319, which is mathematical modeling, then this is something you'll probably come across again in the future. Okay, and at the end of this class I'd also like to go through a really quick example using Octave, or at least how we can use some of the functions built into Octave or MATLAB to evaluate the critical points of these plane autonomous systems. Okay, so we're looking at something today called the Lotka-Volterra equations, which are a really well-known set of nonlinear differential equations, a system of nonlinear differential equations, describing the dynamics of a predator-prey. So we're talking here about, let's just say, one kind of animal that exists, and perhaps it's it's a herbivore, so perhaps it's eating grass. And then there's a second that would be called the prey. There's a second kind of animal called the predator, which is coming to eat the prey. Okay, so the dynamics are the prey can grow because they can eat all the grass and they multiply, but at the same time as they're growing and multiplying, they're being eaten by the predators. So we want to study the dynamics of this system. Most of the content I'm talking about today is almost directly from Wikipedia, because it was probably the best source I could find for this case. So in the simplest case, we're just going to consider a population of species, n, as it changes over time, and we're going to assume that we have abundant food with no predation. So let's just look at the case where there are no predators, it's not being eaten at all. So mathematically we can write this as a first order ODE, and you would have seen this in class before. So if n is the number of the prey here, or the species, the rate of change of the population of the species is equal to r times n. Okay, where r is the survival rate, or really it's just the birth rate minus the death rate. Okay, and of course this is a separable equation, and so it's not too hard to see that if I separate the variables here, I'm going to get exponential solutions. Okay, and it turns out that if r is greater than 0, or in other words, if the birth rate is greater than the death rate, then we get exponential growth of the population. If the birth rate exactly matches the death rate, in other words, r equals 0, then we reach some kind of equilibrium, and we can see that in the equations as well. If r is 0, dn by dt is equal to 0, so we get no growth. We have some equilibrium. And then again, if the death rate is larger than the birth rate, or in other words, r is negative, then we get an exponential extinction of this prey, of this species. So now if we add to this model the case where the population is now hunted by a predator, so n here is the number of the species. I'm going to call capital P. I'm going to let that be the population of the predator, and this constant here, r of p, is the rate of predation. Okay, that's predation rate. So here we have these first two terms. Dn by dt equals Rn. This is our exponential growth equation, or exponential decay equation. So in other words, without predation. So this extra term here, this is basically the interaction of the two populations. The rate of predation, or in other words, the rate at which these two populations contact each other, multiplied by the population of prey, multiplied by the population of the predator. Okay, and so we would have an additional equation for the population of the predator here, and that would be two coupled nonlinear ODEs. Okay, so that was basically by way of motivation. What I'm going to do is, like I said, we can write a similar population growth equation for the predator population. We end up with a system of two nonlinear first order ODEs. I'm going to switch to the notation used on this website here, just to make things slightly easier. And so we can identify these terms, right? So now X is the population of the prey, so the number of prey. For example, let's just say rabbits. Y here is the predator, so let's say foxes, so the number of predators. Alpha here is going to be the growth rate of X, so of the rabbits. Gamma here is going to be the growth rate of the prey, predators rather. And then these other two parameters, beta and delta, these are just parameters that are associated with the interaction between the two species. Okay, so we get a system of nonlinear equations. So nonlinear because we have the x times the y in both these terms here, and these equations are coupled. We have to solve them together. And we're assuming all the parameters are positive, describing growth rates and constant as well. We're assuming these are constant. So this system of equations is known as the Lotka-Volterra or predator-prey equations. So we have a couple of assumptions for this model, and just to list a few of them, we say the prey population finds ample food at all times. So if these rabbits are eating grass, there is tons of grass for them to eat. They're never going to run out. So in the absence of predation, they're going to grow exponentially. We're going to assume that the predators only eat the prey, so the foxes in this case only have rabbits to eat. They can't eat the grass, and there's nothing else for them to hunt. So the foxes are only eating the rabbits. We are going to say, as our equations describe, that the rate of change of a population is proportional to the number of individuals in the population at any time, and we also have to assume that the predators are always hungry. So just because a fox is eaten just an hour ago, doesn't mean it's going to ignore a juicy rabbit hopping across the field. It's going to go get it. Okay, so this model has two equilibrium solutions, or two critical points. So remember, these critical points are where both dx by dt and dy by dt are equal to 0 simultaneously. So if you write down those solutions there, those equations there, basically we're just looking at this second part here. Alpha x minus beta times xy equals 0, and minus gamma y plus delta x y equals 0. Okay, clearly there's going to be one critical point at x equals 0, y equals 0, right? That's an obvious one because this whole equation is multiplied by x and this whole equation is multiplied by y, so there's obviously going to be one critical point at the origin. So if we think about what that represents for a minute, that represents no rabbits and no foxes. Well, if there are no rabbits and no foxes, then they cannot breed, so they cannot produce more rabbits or foxes, and they cannot eat each other because there are nothing to eat, and there's nothing to eat with. There's no foxes, there's no rabbits. Obviously it's a critical point, and we call this the extinction critical point. Okay, but the second critical point is y is equal to alpha over beta, because if you look at this first equation, if y is alpha over beta, then we get beta times alpha over beta is alpha. We get alpha minus alpha is 0. Okay, and then if y is alpha over beta, then, well, x can be anything in this equation. That equation is still 0. But to make this equation 0, x is going to have to be gamma over delta. So if we go delta times gamma over delta, we get gamma minus gamma is 0. So there is a second critical point which depends on the value of these parameters. Okay, and remember, these parameters are always positive. So let's take our two critical points here, and let's study the stability of these critical points and the type of these critical points. So again, we're going to calculate the Jacobian of the linearized system. So in other words, we're going to take this first equation, which we're calling f, which is alpha x minus beta xy, and take its two partial derivatives, one with respect to x, one with respect to y. And then similarly, the second equation, the right-hand side of the second equation, we're calling g, and we're going to also take its partial derivative. So df by dx is going to be alpha minus y times beta, alpha minus y times beta. Df by dy is just going to be minus beta times x, dg by dx is going to be just delta times y, and dg by dy is going to be delta times x minus gamma. Okay, so we have this Jacobian matrix A here, which again is dependent on all of our parameters. Now we want to evaluate this Jacobian at the two critical points. So let's start with 0, 0. So if I substitute x equals 0 and y equals 0, I get these two solutions here. Alpha A, the Jacobian evaluated at 0, 0 is the matrix alpha 0, 0 negative gamma, which of course is a system which we can immediately just read off the eigenvalues, which are going to be alpha and minus gamma. Lambda 1 equals alpha, lambda 2 equals minus gamma. Remembering that all of these parameters are greater than 0, so what we have is two eigenvalues which are of opposite sign, because alpha and gamma are both positive. Okay, alpha could be equal to gamma, so the only way that could be true is if it was 0, right? So then we would have a system where the population doesn't grow at all. So let's assume also that alpha is not equal to 0 and gamma is not equal to 0. Okay, well in that case then we have two real distinct eigenvalues of opposite signs. Okay, so we have a saddle point. So two real distinct eigenvalues of opposite signs. We have an unstable saddle point at the origin. And if you think about it, that makes a lot of sense, because if you are just above the origin, so if your number of rabbits is, let's say, 2, but your number of predators is 0, then your number of rabbits is going to grow exponentially, so you move away from the origin at that point. But if your number of rabbits is 0 and your number of foxes is, let's say, 10, the foxes have nothing to eat, so they're going to die out, so they're going to converge to 0. So it's an obvious saddle point there, where if there are no prey, the predators are going to die out to extinction. But if there are no predators, then the prey can grow exponentially. So there's this obvious saddle point at 0, 0. Okay, well let's check the other eigenvalue now. Let's classify the other, let's calculate the eigenvalues of the matrix, Jacobian matrix evaluated at the other critical point. So at this critical point, gamma over delta, alpha over beta for y. If we substitute those values in there, well, if y is alpha over beta, we get alpha minus alpha is 0, and similarly on the other diagonal. And we get this, this sort of off-diagonal matrix here. You can evaluate the eigenvalues of this 2 by 2 system and find actually that we get complex conjugate eigenvalues. Okay, and these are the values of the complex conjugate eigenvalues. Again, remembering that alpha and gamma are both positive constants. Okay, and in fact these are pure imaginary eigenvalues for this matrix. So if I look at my again my useful information on the stream site, I get an indeterminate stability. I get a center or a spiral point of indeterminate stability. So either a stable or unstable spiral or center. Okay, so I guess I just wanted to show you a real life example of a nonlinear system of ODEs. There are plenty of other examples we could have used as well, but hopefully that at least gives you a little bit of motivation to take mathematical modeling next year, because that's really where mathematics hits the real world. And okay, so for the rest of this class, we're just going to look at how we can solve or classify these critical points using Octave or MATLAB. I'm going to use Octave Online. Okay, so I'll see you in a second. Okay, so now we are going to try to solve a system of equations. Well, actually, maybe I shouldn't say solve. Let's say classify the critical points of the system. And so we're going to look at the system. Well, we've actually seen this system in lecture 35, so feel free to double check my answers here. But we have dx by dt equals negative 2 times x times y, and dy by dt equals y minus x plus x times y minus y cubed. Okay, so we want to classify the critical points of this system. The first step then should be to find the critical points of the system. Okay, so well, how do we do that? Well, we're going to write sol, so for our solution, equals solve, and then here we're going to enter in both of the equations we want to solve. So we want to solve negative 2 times x times y equals 0. Okay, before I do that, I should make this x and y symbolic. So at first I should do symbolic or sims xy. Then I should write solve negative 2 times x times y equals 0 is our first equation we want to solve. The second equation is this y minus x plus x times y minus y to the power of 3 equals 0. Okay, so if I save that and run that, that should give me, well, from lecture 35, that should give me 3 solution points. Okay, and you can actually see, you can't see the points right now, but you can see there are 3 points. So sol 1, 1, 1, 2, 1, 3. So there are actually 3 solutions to this system of equations as we found in lecture 35. But how do I view these solutions? Well, they're stored in this thing that we called sol, and we've got 3 entries here. We've got this entry, we've got this entry, and we've got this entry. So let's just type sol. Well, you can see here that we're in curly brackets. These brackets at the start, end and the start are curly, so I'm going to write in sol in curly brackets 1. So in the entry sol 1, I have an x and a y, a scalar structure containing 2 fields. So I'm going to type sol 1 dot x, and now you can see that gives me the answer 0. Okay, so the way I can find these 2 points is writing sol 1 dot x, sol 1 dot y. Okay, and this is therefore my point 0, negative 1 is my first critical point. Well, we said there was 3, so let's check the other 2. Here I have the point 0, 0, and then the last one should be 0, 1. Okay, so here you can see that this solve function in Octave has found the 3 solutions that we found in lecture 35. So that's fantastic. So now we know we've got point 1, point 2, and point 3 that we have to classify the critical points at these points. Okay. Okay, so now we have to calculate, so we've got a nonlinear system here, right? So we need to calculate the Jacobian of this system. So what I'm going to do is I'm going to type out the 2 equations, f negative 2 times x times y, and g is equal to, what was it, y minus x plus x times y minus y cubed. So I've got my 2 solutions here, my 2 functions here, and I want to calculate the Jacobian of these 2 functions. And how I do that in MATLAB or Octave is using the Jacobian command. So A is equal to the Jacobian of, now I need to put this, Jacobian is surrounded by outside brackets, so we have Jacobian then some round brackets. Then inside the round brackets I'm going to put some square brackets and write f semicolon g. Okay, so that is going to give me the Jacobian. So if I save and run that, then hopefully I'm going to get the Jacobian of the matrix. Add a bit more time there to make sure. Okay, so here is the Jacobian, negative 2 times y, negative 2 times x, y minus 1, and x minus 3y squared plus 1. Okay. But recall that what we need to do to classify these critical points, the 3 that we found, is to substitute in the values of x and y at the critical points into this Jacobian A1. So let's go A1 equals, so what I'm going to do is I'm going to substitute into the matrix A. I'm going to substitute in the variables x and y, so they're in square brackets there. And I want, for the first point, I want to substitute in the point that I found in my solution, sol. So I'm going to write sol in curly brackets 1 dot x, so that's my x component, and then sol 1 dot y for my y component. Okay, and so if I do that, what do I get? Let's see. It'll take a little while to run, but it should give me the matrix. So here we've taken, if you recall, the first point was negative, or was 0, negative 1. It's taken x equals 0, y equals negative 1, and substituted into this Jacobian matrix. So let's do that for all three of the solution points, the critical points. So I'm just replacing the subscript of 1 with 2 there. So we're looking at solution 1, solution 2, and solution 3. Those three critical points. Okay, and now what we really need from these matrix, well actually, let's leave those outputted. What we really need from these matrices is the eigenvalues, right? Okay, and that's a very simple, it's a very simple command, just eig. We know that eig is the eigenvalues of the matrix. So what I'm going to do is I'm going to say point 1 is equal to, I want to print out the point so that I can see exactly which point we are working with. So this is just for visualization purposes. So what I'm going to do is I'm going to write double sol 1 dot x and double sol 1 dot y, and if I've done that right, what this will do is print out the point 0, negative 1. So the point 1, 0, negative 1. So the double just converts this sol, this component of the sol that we're using, into a number rather than a symbolic variable. Okay, so so the point 1 here, we can write down the eigenvalue of a1 is equal to the eig of a1. Okay, and if I do that, what do I get? Well, hopefully hopefully agrees with what I found previously. So here I get, you can see I've got the matrix A1 up here. I've got the point 1 here, 0, x equals 0, y equals negative 1, and the eigenvalues of that matrix A1 at this critical point, point 1, are 2, negative 2. Okay, and if you recall, what does that represent? Well, that represents what did I say? A unstable saddle point. Okay, so if we get real distinct eigenvalues of opposite signs, then we get an unstable saddle point. Let's check the other points now. So point 2. So again, I'm going to be representing or printing my point 2, which was 0, 0. And I'm going to look at the eigenvalues of matrix A2. So let's save and print that. So at the point 0, 0, so point 2 here, 0, 0, we get the eigenvalues 0 and 1. Okay, so because we got an eigenvalue of 0, just like in our class, in lecture 35, the test is inconclusive. So this classifying critical points does not work if one of the eigenvalues is 0. Okay, so that's exactly the same as what we found in class. And point 3 here, let's just do that for completeness. So again, we're going to print out point 3, and then for the eigenvalues of matrix A3, which is the Jacobian matrix with point 3 substituted in. And hopefully we find a repeated, there we go, a repeated eigenvalue, a negative, in fact it has negative sign, right? So this was our point x3, x2 from lecture 35, and we said it's either a stable, it is stable because both of the eigenvalues are negative, and it's either a stable node or a stable spiral point. We can't do any better than that. So hopefully in this file here I can show you how to solve simultaneous equations using using Octave. B, how to calculate the Jacobian of two functions. C, how to substitute in the values of those solutions from sol, the solve command. And 4, of course, you know how to find eigenvalues using Octave, because we had to do it, or at least I've shown you an example in an earlier class. So this is how we can find and classify critical points of nonlinear systems using Octave. Okay, thank you.